Alright, so we saw the implication of rank nullity theorem for T from V to V. Alright, we saw that V finite dimensional, that's very important, that T is 1 1 if and only if T is onto, if and only if null space of T is a 0 vector. Fine. Now we want to talk of what is called isomorphism. So earlier we had in our school days what is called bijective. Two sets are in bijection if there is a map from one to the other which is 1 1 and onto. So we have a notion of here what is called definition of isomorphism. Isomorphism. So let V and W be two. You can define it for infinite also, but I am looking at only finite dimensional, two finite dimensional vector spaces over Vf, all right. Then V is said to be isomorphic to W, all right, or V is isomorphic to W, that is the notation, isomorphic to W, if there exists a linear transformation T from V to W such that 1 T is 1 1, 2 T is onto. Is that okay? So you can see that in some sense I have used these ideas somewhere. So we are saying that two vector spaces are isomorphic, all right, if I can get a map linear transformation T from one set to the other such that T is 1 1 as well as onto, all right. So the idea of isomorphism basically means I have not used the word what is called a homomorphism, but I have said it is a linear transformation. So there is a notion of what is called homomorphism. I have not used it, but basic idea it is of linear transformation itself. T of x plus y should be equal to T x plus T y, because there are two operations here. T of alpha x is equal to alpha T x, all right. So they are already for linear transformation, hence things are okay. So I will not prove it, but I will look at some examples to show that what I am trying to say. Examples, all right. So first example is, let us look at this R3 or R2, and I want to look at this vector space V, which is all x, y, z belonging to R3 such that z is 0, all right. Look at this. So here if I look at, since z is 0, any vector here V has the property that it looks like x, y, 0, fine. So I can define my map f from R2 to V by f of x, y as x, y, 0, all right. So this will imply that f is 1 1, because you can see that the kernel or the null space of this map, null space of f is f of x such that x belonging to R2 such that f of x is 0, all right, which is same as x belonging to R2 such that x, y, 0 is 0 0 0, which is same as x is equal to 0 or x equal to 0, x, y belonging to R2 such that x is 0, y is 0, which is the 0 vector itself. Is that okay? So the null space is 0, therefore the map is 1 1, all right. So f is 1 1. What about onto? Onto, take any vector here. So any element in V has the property that, what is the property? That Z is 0. So, any V, if I take in V, then V is x y 0, all right. Its pre-image is x y itself, fine, as f of x y is equal to x y 0, all right. So, it is onto, fine. So, the behavior of these two are same, that we already know, that this gives us the xy plane. So, they are same as such, there is nothing special, we have already known it. So, I have not given you anything special here, fine. But what I would like you to understand here is that they get related. So, here the dimension of this space is also 2, all right. So, some more examples to have a better understanding. So, again R2 here, V is R2 and another space W is x y z W belonging to R4, such that x plus y minus z is 0 and y plus W is 0. Suppose I am looking at this, fine. So, if I look at this, it tells me here that the matrix that I am looking at is 1 1 minus 1 0 0 1 0 1. I am looking at the null space of this. So, this I can write it as 0 1 0 1, 1 minus 1 is 0, minus 1 I hope this is RREF I think, this is 0 minus 1 all right. So, therefore, the solution of this that I want to look at any V here is of the type x y z W. X from here is nothing but, look at these 2 points, this is nothing but z plus W, fine, and y is minus W, z and W. So, this gives me the vector z times 1 0 1 0 plus W times 1 minus 1 0 1, fine. Check that these two are elements there itself. So, 1 and 1 is 0 and that is okay, there is 0 0 and 1 minus 1, yeah, it is 0, fine. So, these are the basis of W. So, the basis of W is 1 0 1 0 and 1 minus 1 0 1, fine, this is the basis. So, I can define my map F from W to R2 by f of 1 0 1 0 as 1 0 and f of 1 minus 1 0 1 as 0 1, fine. Then you can see that f is 1 1. So, I am going to define f using this. So, what I am saying is that I want to define f of, for any V belonging to W, I have to define this. So, any V here is some alpha times 1 0 1 0 plus beta times 1 minus 1 0 1. Any V is of this form. So, I define this as f of V as alpha times 1 0 plus beta times 0 1, which is alpha beta. Is that okay? So, for every V belonging to W, I write V as this. Is that okay? That is important. I am writing this first using linear combination from here basis, and then I am taking the maps. And therefore, this is a linear transform because I am looking at the linear transform here. I am looking at 1 0 0 1 times alpha beta, and here it was looking at the vector 1 0 1 0 1 minus 1 0 1, this matrix times alpha beta, all right. So, basically it is this alpha beta, all right, this alpha beta which is playing the role here. Is that okay? So, you have to be careful here. So, you can see that f is 1 1 because of this part, because if you are saying that 1 1 means the images has to be 0. So, this part has to be 0, this is what will happen, all right. So, we will imply that. So, look at null space of f. So, where is null space of f is 0? When this is 0, alpha is 0, beta is 0, so you will get a 0 vector here. Is that okay? Dimensions of the two are same. Dimension of W is 2, which is same as dimension of R2, and therefore, by the rank nullity theorem, theorem, f is onto, fine. Or you can do it directly also using this idea of the function itself, like given you the actual function, fine. So, you can do that yourself, fine. So, as a corollary of things, I will just write some things here that I would like you to remember and understand. Corollary: the following statements are equivalent. The following statements are equivalent for a linear transformation T from V to V, where V is finite dimensional. All right. 1, T is 1 1, 2, null space of T, which is same as kernel of T, is 0, 3, rank of T is n, which is same as dimension of range of T, 4th, T is onto, which is same thing as saying that, all right, I have already said dimension of range, T is onto, T is an isomorphism of V to V itself, all right, V to V itself, different basis. 6, if V1, V2, Vk is a linearly independent set, then T of V1 till T of Vk, all right, is also linearly independent. That's important. So, it takes, so T is 1 1 means T sends linearly independent set to linearly independent set. Is that okay? That is important. So, if you remember, what we had proved earlier was that if V1 to Vk is linearly dependent, then T sends dependent to dependent. Now, what we are saying here is that whenever T sends linearly independent set to linearly independent set, implies and is implied by T is 1 1. In some notion, what you are saying is that T is invertible. All right. So, these things gets related. All right. Inverse in terms of matrix, you had similar things. So, you need to understand these things. So, when I say that T is invertible, I have not given you the idea of invertibility as I said. So, what you are saying is that there exists S from again V to V itself, such that SOT is the identity function, which is same as T composed with S. I think I have not defined the identity function for you, I forgot to define it. So, identity function basically means that, so identity function from V to V is identity of any U is U itself for all U belonging to V, all right, fine. So, what we are saying is that I have an identity function which sends every element to itself, that is all I am saying, sends every element to itself. Is that okay? So, we have defined what is an identity map. Identity map is identity of V is V for any V belonging to the vector space. So, it will depend on which vector space you are looking at. We have definition of this identity map, that is all, nothing else. So, recall that if you are looking at x belonging to R2 and you have map ID from R2 to R2, then ID of 1 comma 2 is 1 comma 2 itself. Is that okay? If I have got identity map from say R5 to R5, then identity of say 1, 2, 3, 5, 0 is basically equal to 1 2 3 5 0. So, it is the identity map, all right, nothing else. Now, we are also, so I think I have forgotten the notation related with L of VW. So, this was all linear transformations from the vector space V to W, fine. So, we would like to say that, so claim if dimension of V is n and dimension of W is m, then L of this in some sense corresponds to, so V has dimension n, so it is corresponds to Rn here, this corresponds to Rm, and therefore, I get a matrix which is of size m cross n. So, it is a collection of all matrices, collection of all m cross n matrices. Why all n cross m matrices? Because if I want to define any linear transformation T from Rn to Rm, T of x is equal to A times x. This x is n cross 1. So, this has to be m cross 1. So, that the total product defined to be equal to 1 cross m, and Tx is an element of, so this belongs to Rm. So, this has to be m cross n. So, the matrix multiplication makes sense, and therefore, this is what we need, all right. So, let us look at the idea here, what I am trying to do here. So, what we want to say is that if I want to look at R of R2 to R3, fine, then I am looking at linear transformation, collection of all linear transformations from R2 to R3. So, as shown here, T will corresponds to something like, so I have to take x and y here. So, there will be two things, but I want three components here. So, I will have something like A11x plus A12y, A21x plus A22y, A31x plus A32y. This is how I get an element of R3, this is an element of R3. I can break this up as A11, A12, A21, A22, A31, A32 times xy, fine, and therefore, T is basically corresponding to this part, fine. So, what I would like you to see here is that this matrix A, which is A11, A12, A21, A22, A31, A32, this corresponds to this following, that it is A11 times a matrix which is 1 0 0 0 0 0 plus A12 times 0 1 0 0 0 0 plus A21 times 0 1 0 0 0 0 plus A22 0 0 0 0 1 0 plus A31 0 0 1 0 0 0 plus A32 times 0 0 0 0 0 1, all right. So, important here is that this one is the 1 1 entry, this entry is the 1 2 entry, this entry is the 3 1 entry, and this is the entry 3 2. That is the way to remember it. So, what we are trying to do here is, if you look at, it is nothing but A11 times, so this is the first matrix, just look at, this is the matrix that I am looking at, 1 0 0, and this I am multiplying by 1 0. Is that okay? So, I get here this part. Here it is plus A12 times 0, this is still the same thing 1 0 0, but now I am multiplying it by 0 1 here, fine. So, this one corresponds to this one, that is, this is E1 for you, things like that. So, if I am looking at A21, 2 is here, so I need to look at A2, this is your E2 for you, this is your E2, but it is in 3 dimension because in R3, and then I am looking at 1 here, so 1 means 1 0 that I have. So, this product will give you this part. Similarly, A22, again this is 2 itself, so it will be 2 here, E2 here and E2 here. Similarly, A31 times E3, this is E3 times 1 plus A32 times 0 0 1, and 0 1 here. Is that okay? So, what we can see here is that these matrices that I am writing here, these matrices, if you recall, they were nothing but Eij. They were, so 1 is less than equal to I, less than equal to 3, and 1 is less than equal to j, less than equal to 2. These were the standard basis of R of, so this is a matrix of size 3 cross 2. So, not R, I will say the matrix of size 3 cross 2, 3 cross 2 matrices over R or over C, whatever you want to see. So, what I was saying here is that every matrix here or any linear transform here basically looks like a matrix, and that matrix can be written in terms of this basis, ordered basis, and therefore, this is isomorphic to L of any vector space V and any vector this, where V has dimension 2 and W has dimension 3. Is that okay? That is all. Thank you.